All right, so we're going to continue looking at probability today. We're going to look at a few different parts of it today. We're going to look at something called conditional probability, and then we're going to talk about events being independent, which is very similar to mutually exclusive, except it's just with multiplication. So, all right, so let's do something really simple. What are the odds that I'm going to roll a 5? 1 out of 6. Very good. So the probability of a 5 is 1 out of 6. What's the probability that an odd number is going to come up?
I mean, 1 half. Yeah.
3 out of 6. Yeah, or 1 half.
Yeah.
All right. What's the problem? I'm gonna write this. What's the probability of a 5 coming up given that I've already got an odd number? Very good. So conditional probability is where we're looking at an event, and then we're looking at that event in relation to another event. So if I know I have an odd number, the odds of me getting a 5 is 1 out of 3 because there's 3 odd numbers. Okay, so we're not going back to the total. That conditional probability is going to basically replace my bottom. So conditional probability is the probability that event B occurs given that A occurs already. And it's denoted as, like I put here, with that line in between it. That's probability of B given A. These are actually the kind of things that we see quite often. It's like you'll talk about what's the probability, or one of the ones we're going to look at later on is what's the probability of a Democratic or a senator from California given they're a Democrat. It's like you're not looking at all the senators, you're just at the Democrat ones and then pulling out the ones from California. So it's looking at the combinations of them. Or what's the probability that a person's a male given that they're a teacher? It's like we look at those conditions quite often. All right. So, actually get the exact name of it. This is a chart. It has a breakdown of a bunch of different pieces in it. So it's talking about what's this? The types of professors and their ages. One second. I gotta open up something real quick. Because I didn't have the questions attached to it. Here we are. All right, so looking at the table, what are some things you notice? Okay.
Oh no.
Yeah, there's. So one of the things, so this is known as a contingency table. So we have columns and rows. And then we have the totals for each of those. So what this helps though is a lot of times when we're looking at conditional probability. Before, on Tuesday, when we were looking at probability, we were looking at it always out of the totals. So now, if I said, what are the odds that I'm going to get a associate professor if they're under 30? Which one was the second one I said? Under 30. So then it's out of 68. So that the order actually really matters in this respect, right? So if I said, what is the odds of me getting somebody under 30 if they're an associate professor, then it would have been 3 out of the 381. But the way that I stated it was 3 out of the 68. So it's really a matter of which one comes first, which one comes second. Okay. But the contingency table allows me to see all that breakdown of data. All right, without having to actually come up with a bunch of them. So the subscripts that I have, so you have the R1, the R2s, those things, the breakdowns there. So those give you the ability to write your simple probabilities without actually having to say out the whole thing. So if I had A2 given R4. So we're looking at that one. So my top number is going to be 17. What's my bottom number going to be? 33, because that's the second thing. And the total of the instructors was 33. Okay. So that's the probability that a person is in their 30s and given that they're an instructor. Now, if I said, here's where wording matters. If I said A2 and R4, that's still 17, but it's out of 1164. If I said, if I'm looking for a person in their 30s and an instructor, then it's 11 out of 1164, because that's now looking at the total. It's no longer conditional. I'm looking at the person having to be both of those things. Okay. If I said, A2 or R4, now we're looking at those numbers, because that's the or. Now, are these mutually exclusive? So when we're doing the or, we're adding those two, right? But we have to do what, since they're not mutually exclusive? We're going to subtract that 17 because that's the overlap. So I would do 402 plus 33, which is 435 minus 17. So 418?
402 plus 33 was 435, like you said.
Yep, minus 17.
Minus 17, you get 418.
Okay. And then that would be out of the 1164. So we're looking at the exact same two things, but how the question's worded and how they're looking for it changes the answer quite a bit. Okay. That's why when you're looking at how things are worded, especially because most of these are going to be word problems and things like that, that's the wording is important.
Building on each other, or can they stand independently?
Oh, they can be independent questions. It really depends on what you're looking for. So the ands and ors, a lot of times, that's typically what you're going to see quite often in like math problems because they're simple, right? And they work really well with like games and stuff because that's how they play. However, in reality, conditional probability comes up a lot more because you're looking at a subset, a subgroup, basically. And you're saying, well, how many of the people in that group are this? So that comes up a lot. So especially when you're trying to break down like how to pick people and stuff like that. The other thing is that those probabilities, when you find them, don't always add up to 100 because you're now not looking at the same totals. Your bottom number is changing. So like that first one where we said age 30, given that they're an instructor, my bottom number is 17. So if I already know that they're an instructor, my odds of picking somebody that are in their 30s is over 50%. And actually, if you go across, I think, except for full professors, the 30s actually is the highest of all of them. All right. To determine conditional probability. This is the exact formula for it. It's basically what we just did. It's the P, A, and B. So it's where they both are. And you're dividing it by the probability of the A, the given event. Now, just because this is a math class and we have to qualify things, the probability of A can't be 0 because we can't divide by 0. However, if the probability of A was 0, the event would never occur, and you just say the event would never occur. Unlike algebra class where you'd say it's undefined. So now if we look at that compared to what we just did here, it was the probability of both of them, which was the 17. That's the and. Over the probability of A, which was 33, because there's 33 of those. Now, technically, the way, now that's, huh?
I'm so tired, it like just hit me. I was like doing, like adding and subtracting. And
So-
but by now I'm like, oh my God, it's not that complicated.
It-
Just follow, I know.
Yeah, it's not.
But anyway, it just clicked.
So just because, actually, you know what? I'm not even going to show you that because honestly, the way that I explained it works fine. And I highly doubt the vast majority of you are going to go love fractions and want to understand why that works. So that's how it is. Because technically, each of those are fractions. So you'd flip over and cancel out the denominator, but we're not going to do that. All right. Questions? Nope, I deleted the questions. So this one, we have marital status and male and female. Come on, questions. Oh, I had this twice. All right, so the first thing we're going to do is, so we've got our questions here. Let's work out how this looks from the wording. It says, determine the probability that the adult selected is divorced, given that the adult selected is a male. So we have the probability of A and the probability of B. So what's A? What's A represent in this situation? A is male. Remember, it's P, E, A. So this one, the given, the adult's male. That's A. Right. That's why I did it this way. Because most people go, oh, it's A and then B. But,
Yeah.
right. But normally when people think about it, it's A then B. Because that's alphabetical. We're things of patterns. We like things that are in order. As much as some people think like, oh no, I can like chaos. No, everybody likes order. As much as we fight it, we like order. We like things that are in numerical order. We like things that are in alphabetical order. It's like we try those things. So your mind is going to switch the A and the B quite often. But it's B given A. And the reason it is that way is because what we're given is actually what we're starting with. Yes.
Depending on the phrasing of the question, after be ordered A, B.
It could say, given that the adult selected is male, find the probability that the adult selected is divorced. It could be. The keyword is given. Yeah. The keyword is given. This is the word you're looking for, because that's basically setting your base probability. That's setting your bottom. Yes.
Given is in there, then is it one of the other ones that we were talking about?
Typically it'll say and those type of things. So what's B in this situation? The divorced. Okay. So now let's go back. So male, the total for male is 0.485. So my bottom is 0.485 because it's P, A, and B over the P of A. And then the and, too far back, is male and divorced. So that's 0.044. So when you divide those, we get 0.091. So that's the probability that an adult selected is divorced, given that the adult selected is male. Yes.
What's the unit on %?
It's probability, so it's division. It's just been divided, so they're not in percentages. So your percentages is once you just take that number, you just move the decimal 2 places. what they did is actually in this problem, unlike the one we looked at over here, these were counts. These are the number of people. So to find the probability, we actually had to do the division for. In this one, they already found the probability of each of those events occurring in the total population. And now you're looking for the conditional probability. And you can tell that because my total right here is 1. That right there tells you that this is all a probability. All right. All right, do B. All right, there's your numbers. So what's the bottom number?
Oh, 4.
Because I'm given divorced. And my top number is still the same, actually. It's 0.44. 0.044. That's right. Yeah. So this one comes out to be 0.423. So the first one we did came out to be 9.1%. So that says that, because these numbers are from the United States. So in the United States, 9.1% of adult males are divorced. Okay. The second one that we just did here says in the United States, 42.3% of divorced adults are male. They sound very similar. Okay. This goes back to wording and how you want to present your data. They both sound very similar. First one says 9.1% of adult males are divorced. The second one says 42.3% of divorced adults are male. Just depends on how you want to present your data. If you said both those to just a layperson who doesn't actually have any understanding of data or numbers, they would assume that somebody screwed up because they're basically saying the exact same thing.
Right.
Yeah.
It's the same question.
Yeah. But the data comes out drastically different. And then depending on how you want to present your information, depends on how you go for it. So one is out of basically all the divorced people. So it's like it's looking at that piece of the population and then you're looking at the divorce rate. So and the second one is looking at your divorced and then looking at your population. And since up until recently you only had male and female being looked at, it's like it's pretty much 50-50. There's actually more females in the United States than males, but it's close. So you'd expect the divorce rate to be pretty close to the same. So all right. Let's see, did I have another one of these? No. Let me actually do one more of these.
Everyone on the dating site, you put up like a tiny percentage that were never married. If you were gonna date, everyone's divorced. The ones that are married are the most screwed up in the dating site. If you're gonna find someone to date.
Yeah, like if you look at this, so I don't know what year this was done, but less than or just about a quarter of the population's never been married. So if you're just literally looking for a single person who's never been married, it's a very small chunk of people. Now, if you looked at this in terms of an age range, it's going to change that a lot too. Like your younger populations are probably going to be more single than your older population. So if you're looking at the entire population, that's what you're going to see. So again, it really depends on how you look at your data and how you look at your numbers and how you want to interpret that information. So, and that's why when we start looking at all this information, it's very difficult for people to understand what the things are because you're getting a snapshot of what's going on instead of all the actual data. Why do they not have oh, that's why. I'm like, why is this not? Because I'm looking at the wrong section. I'm like, I'm looking for a table like this because I want to give you guys some more so you can look at like the wording and stuff. And I'm like, this is not what I wanted. This is better. Like this one. All right. So these are actual counts, not probability in this case. So you're looked at discrepancies between what a victim of domestic violence requests and what the courts were rewarding. The following contingency table cross classifies by race and gender a sample of 407 domestic violence protective orders in North Carolina. So these are protective orders that were granted. All right. So what's the probability that a protective order was granted given that they were Black?
47 to 37.
So that's the 147 out of the 407. What's the probability that a protective order was given if they were a white female? Right. That's very important. We're still out of the total. That's an and. Okay? They didn't put the word and between it, but it's an and. You're looking at white and female. What's the probability of a male being granted a protective order if the filer was white?
It'd be the other way.
No, it's 30 out of 240. So 30 is the male and white, and the white was 240. What's the probability that a male was granted a protective order given that the filer was Black?
Oh no, 26 out of 147.
Right. Again, the Black's total, so that's the 147. What's 30 divided by 240? What was it? What's 26 divided by 147? What was it? 177? Somebody quickly do 210 divided by 240. Do 121 divided by 147.
22, 3, 22, 3.
Okay. So here's if you're just looking at numbers, so forget probability, totals, and stuff like that. You go the percent of protective orders that were granted for white men is 0.125. Or if you did this, the 30 out of the 407, you did 26 out of 407. You'd say, okay, well, white men are getting more protective orders than black men. If you looked at it in comparison to how many of those that were granted in that race, you'll notice that it's not. They're granted at about the same rate. So that's where the probabilities and the conditional probabilities can help you see what's going on. Okay, if you're looking at it in terms of the totals, even now in the United States, we're still about 62% white. We're about 19% black, and I think about 17 or 18% Hispanic right now in the country. So your total numbers are going to look small in that respect. But when you look at it compared to the race and compared to the other one, so you're looking at the same portion of the population, then you can start to compare across things. Okay. So that's where you want to start looking at conditional probability, where it starts to really help understand some of that data behind the things. That's where when a lot of the police violence and stuff like that was happening after really early in the morning. George Floyd. Yeah. Well, that was the first. I'm like, I know it's not that. That's what I'm like. It started with an F. Happened. There was a lot of data that came out and goes, well, police are shooting whites at a higher rate than blacks. And it was like, no, they were looking at total numbers. And if you look at total numbers, when they're 3 times the population, you're going to have that. But when you look at it as a conditional probability inside the population, you start to see that drastic change in it. So that's where the power of conditional probability comes into play, because it really helps you start to comparing data, which is what statistics and stuff is supposed to really help you with. Is how can you compare data in a way that helps you understand the situation. So, and percentages and probability allow you to start to break down those numbers and get it into a comparison value, because you can't just look at the total numbers, because it just doesn't work that way when populations are not equal. So you could when you're looking at just like male and female, because they're pretty much equal. But once you get past that, it's like it's very difficult to be able to compare just by looking at total numbers.
A black woman to a person had less complications from a black provider than a white provider, which is mind blowing. I'm not sure why, but that's one of those statistics that's like,
yeah,
no, it's like, what the heck is going on?
Yeah, it's like, and sometimes there's lots of reasons why it could happen. It's just a matter of we're just looking at research, and it's like we don't know. So, but the nice thing is now we're starting to ask those questions. Yeah, it's like we're also starting to ask those questions now. It's like where before we weren't, and that's really, really important that we're being able to have those conversations. All right. So we looked at the general addition rule last class. Addition is when there's ors. It's this or that. We add up those possible things. And then we had to subtract off any piece that was overlapping. When we're looking at an and, we have to do multiplication. Now, if you think about, I'm going to come back to the screen in 1 second because I want to show you the other screen, because this was just basically a little bit of algebra. Notice how this formula was division. All they did was, we want this. We just multiply both sides by the P of A. Because that's what we want. We want the and. So to find the probability of two events and those two events being combined, we do P of A times the conditional probability of B given A. Now, these rules come up when we don't necessarily already have the and. So when we're looking at the data, like this data, we already have the and. Like white females, that's and. So we know there's 210 of them. So we already have that and. This formula comes into play when we don't necessarily have the combined things. We're looking at distinct data overall, and we're looking at, well, where's the overlapping piece of those? All right. So U.S. Congress, this is the 113th Congress. I think we're on 119 now. 118th. I was one off. Every 2 years it goes up. So the composition of Congress and the congressional directorate. For the 113th Congress, 18.7% of the members are senators. 53% of the senators are Democrats. What is the probability that a randomly selected member of the 113th Congress is a Democratic senator? Okay, so here's a couple stupid questions before we go on. How many members of Congress are there? Does anybody actually know?
Two senators, yeah.
Yes,
So 437.
almost. It's 435. You were. So 435 plus 100. It's 535 members. So there's 535 total members. And 100 are senators. You don't actually need this for this problem, but it's actually kind of nice to know. When we have our presidential election, we have 535 electoral college votes. That's where that number comes from. It's how many senators and how many representatives each state has. So Connecticut has 5 representatives and 2 senators. So we have 7 electoral votes. California has, I think, 43 and 2, so I think they have 45. I think they have 43 representatives. Wyoming has 1 representative and 2 senators. So they have 3 electoral votes. And they have about 705,000 people that live in the state. So this is where the fight comes in, where they're talking about popular vote versus electoral college votes. Because an electoral college vote, actually, some states' electoral college vote has, each person has more say in it. So in Wyoming, each vote's worth about 250,000 people. In Connecticut, we have 3.5 million people. We have 7 votes. So each vote's about 500,000 people. So it kind of favors the smaller states get a little bit more say, but that's actually the way Congress was set up with the senators, is that they didn't want the large states to completely overwhelm and basically have mob rule over the smaller states. So now the state of Wyoming, which we always pick on the state of Wyoming, has more actual size than the entire New England. All of New England is smaller than Wyoming. It's literally crazy. Like when I drove cross country last summer, we drove across North Dakota, and it took me 9 hours to drive across North Dakota. You know, one straight highway, 9 hours. I can get to Quebec in Canada in 6. So it's like, it's just, it's mind blowing that the size difference in it. And then there's just not a lot of people out there because we like being around other people, so we tend to go towards the coasts, and that's where the majority of our populations are. So when they start having those arguments and stuff like that, because they're going to come up in next year when we have our presidential elections, the same arguments are going to come up again. Is that's where some of those arguments are coming from. It's like, how do we balance that? All right, back to the question. It always comes down to Florida. Actually, it was last time it came down to 6 years ago now. It came down to Pennsylvania in like not Wyoming, Wisconsin, like that. It was the Iron Belt, as they call it. So, all right. So for the 113th Congress, 18.7% members were senators. So if you did 100 divided by 535, you get 18.7. That's actually where that came from. And 53% of the senators are Democrats. Anybody know the breakdown of the Senate today? Who has control of the Senate? So if by control, you would assume they would have how many votes? At least 51. That would make sense. They're at 49. Yes. We have there's 49 Democrats, 49 Republicans, and 2 independents. The independents both caucus with the Democrats, which is what the Democrats have control over. It's Bernie Sanders and one of the ones from Maine.
Oh, I remember you saying this a different time.
Yeah. So it's again, those little interesting things. All right. Yeah, pretty much. Bernie Sanders has 3 houses. So just remember that when Bernie Sanders keeps saying you have to give money back to the people. He has 3 houses, and his biggest one I think is worth like $2.5 million. So I have very little use case for the government as a whole. Yeah, it's like, all right. So the question's asking, what's the probability that a random selected senator as a Democratic senator? So we want the probability that it is a Democrat and a senator. Okay. So we are looking at the probability that they're a senator times the probability that it is a Democrat given a senator. So what's the probability that they're a senator? Or what's the percent? Yep, the 0.187. And what's the percent or the probability that they're a Democrat given they are a senator? That's the 53%. I will use an X even though I hate using X's for multiplication. I just don't feel like writing percentages. Yes, or probably or
Do you always want us to write out and, or can we use the ampersand?
Oh, you can use the ampersand. I just suck at writing the ampersand. So that's why I wrote it. I keep going. I'm like, nope, I'm going to screw up writing it.
Yeah, that's me as well.
Yeah, so it's like I just write out hand. So we multiply these, and we get 0.099 or 9.9%. So if you have all of the congressmen and women standing in one room, and you're going to go randomly select a person. You have a approximately 10% chance of picking a Democratic senator. Okay? That's what that says. So the difference is the given one is out of that population. So there's a 53% chance that you'd grab a Democrat if they were just the senators in the room. But once you add in the House, now you only have a 10% chance of picking out a Democratic senator. Okay. So the conditional probability is limiting the population, is basically what it's doing. All right. Let's get that one. All right. Independent events. So they're determined to be independent if the conditional probability is the same as the actual probability. So if they're independent, the given condition doesn't have any impact on it. So let's go back to playing cards. So event K is a king is selected. Event F is a face card selected. So what is the probability that a king is selected? So what is the probability of a king? 4 out of 52, which is what as a decimal?
0.07.
Yeah.
Did I say that?
Yeah, she did. That's okay. That's why when you said it again, I'm like, wait, she said that already.
I'm checking. My phone.
All right. So if they're independent, me taking the king given a face card should be the exact same number. What is the probability of me picking a king given that I've chosen a face card? It's 3, or no, it's 4. Yeah, there's 4 kings. It's 4 out of 12. So yeah, it's 4 out of 12, which is what? 0 or 0.333. So they are not the same. So events K and F are not independent. Okay. So we already know the king is 0.077. So what's the probability of me picking a king given that I've chosen a heart? One out of 13. What's 1 divided by 13?
0.077.
So those are now the same, right? So that's independent.
And by saying you mean they have the same collection of outcomes essentially? right?
No, actually, no. That's a very important difference in what we're saying. The first one, if I'm picking a king, just picking a king, right? I have the king of clubs, king of hearts, king of spades, king of diamonds. So my outcomes, I have 4 kings. Okay. When the second one, if I'm picking a king, given I've chosen a heart, I'm literally picking one. It's just the king of hearts. So my outcomes are not the same. The probability of that event happening is the same. Okay. So the probability of me choosing a king out of my entire deck of cards is about 7.7%. The probability of me picking a king given I've had the hearts is 7.7%. So that is why they're independent, because the probabilities of either event happening is the exact same.
So let me get this straight. In short, you're saying that choosing a king
Yep.
and choosing a king of hearts are two distinct events that do not affect each other. So they're independent, right?
It doesn't affect the probability of the event happening.
Okay, so are they independent, bro?
Yes. Oh, yeah. They're independent because the probability is the same.
Okay, that's just what I wanted to
So you're not necessarily getting the same cards out, but the probability of those two events happening are the exact same. So based on the criteria of independence, these two events are independent. The reason that's important is because remember what we were talking about with the multiplication. If the two events are independent, remember back to the addition and subtraction. If they're mutually exclusive, I didn't have to worry about that subtraction piece, correct? So if they're not now we're looking at multiplication, if they're independent, I don't have to worry about that conditional probability because they're independent. I can just multiply my two percentages and I'm good. All right. So we have to determine if they are independent before we can do that. Now my little note down the bottom, wording. If you see the word or, you're adding. The term and is multiplication. All right, we'll play roulette. In roulette, all events are independent. No event, the events do not impact each other. Okay. So, since we know they're independent, we can just multiply their events together to find out the probability of that occurring. So, in 3 plays of the roulette wheel, what's the probability that the ball will land on green the first time and black the second and third times? So, what is the probability of it landing on green? Yeah.
Question, how is independent different from mutually exclusive?
It depends. They're not really.
Oh.
One's addition and one's multiplication.
Okay, that's the only difference?
So when we're looking at addition or the ors, it was literally the overlap of the two pieces. Okay. So when we're looking at mutually exclusive or when we're looking at independence and multiplication, it's the conditional probabilities. They're basically the same. So, and honestly, if they're the same, it doesn't matter which one you use. So if you were thinking back to the original problem or original multiplication, it was the probability of B times, or probability of A times the conditional probability of B given A. And if B given A is the exact same as B, then it's just the probability of B. It just makes our life a little bit easier. Most situations where we're looking at it, you're going to look at a situation like this where the events don't have any impact on each other, which is the exact same as mutually exclusive. So since I'm playing the 3 roulette, I want to know the total probability that these 3 things happen. It's not an or, it's a and. Like I want this to happen, then this to happen, then this to happen. So what's the probability that it'll land on green? Yeah, 2 out of 30. I'm just going to keep them all as 38. 2 out of 38. So that's the first event. What's the probability that I'm going to land on black?
18 out of 38.
18 out of 38. Not 1/2 because of the green. And what's the chance I land in black again? 18 out of 38. So when we multiply those three together, we get a 0.12. So 1.2% chance that that happens. Now it's interesting when you look at independence on roulette's an easy way to look at this, because if you sit there and go, okay, I'm going to play black, and then I'm going to play red, and then I'm going to play black, and then I'm just going to keep switching back and forth. You're going to win just exactly the same amount of money if you've just left it as black, because the probabilities are the exact same of those two events happening. Every time they spin the wheel, the probabilities of the black hitting or the red hitting is exactly the same. So those people who switch back and forth are the exact same as the people who put the money on one and leave it there. Doesn't change your probability.
Have you played with?
Yeah. I play the numbers inside though.
Has there been a probability to pick numbers? Or-
No.
Okay.
That's the roulette. Remember we said craps is the best game to play at a casino because you got the best odds?
Yeah.
Roulette's the worst, actually. Because the actual, so there's something called expected value or expected winnings. It's what you'd expect to win by playing. And roulette's got the lowest number. Actually, the only thing worse is the actual slot machines. So the slot machines are basically just give the casino your money. All right. Some people win. The vast majority of people lose. Yeah, let's do this couple real quick. Actually, you know what? Yeah, we'll do this next time because we're almost running out of time. All right. So the only thing I didn't cover, I did up through 5-6. So we did 4-3, 4. We did 4-4, 4-5, and 4-6 tonight, or today. The only thing I didn't cover was 4-8, and I wasn't doing Bayes rule anyway. So I will cover that one quickly on Tuesday. Because we need to know combinations and permutations. So, all right.
On the syllabus, you've written that Bayes rule starts section 4.6 when in reality
It was
starts
4.7. Yeah, I know. And I'm not covering Bayes rule at all.
Okay.
It was an old the syllabus I originally wrote was from an older edition of the book.
Okay, so don't worry about
Yeah.
Bayes rule.
Nope. All right. Have a wonderful weekend. I will see you on Tuesday. And it's almost March. What's up?
I won't be here on Tuesday because I have a doctor's appointment.
Okay.
So are we just gonna be what are we gonna be doing?
I'll quickly do 4-8, which shouldn't take long, and then we're going to go into chapter 5.
Okay. And how long does it typically take you to post the?
I'm going to go
Classic.
post about 30 minutes after class. It just depends on how fast Google sends me my Meet document.
Okay.
So, but it should be posted about 30 minutes or an hour after class.
If I
we've
have any
been-
questions, am I okay to email you?
Absolutely.
Awesome. I like to email.
Yeah, not a
you.
problem. Welcome.